Hello everyone, this is Dr. Kavita, Assistant Professor of Microbiology, Sadakathil Lapa College, Tirunelveli. Today's topic of discussion is Historical Account of Microbes in Industrial Microbiology. Industrial microbiology is the study of large-scale production of microbes or their products for direct use or in the creation of other value-added products. Let's learn more about the various phases in the history of industrial microbiology. The field of industrial microbiology has evolved over centuries and we can trace its progress through five major phases. Phase 1, that is alcoholic fermentation period, up to 1900. This phase primarily focused on organisms, particularly yeast, for alcoholic fermentation. Fermentation of alcoholic beverages such as wine, beer had been practiced for thousands of years, but the scientific understanding behind the process only emerged in the 19th century. Louis Pasteur during 1857 made a groundbreaking discovery that microorganisms like yeast were responsible for the conversion of sugars into ethanol through fermentation. He also demonstrated that spoilage of wine and beer was caused by unwanted microbes, leading to the development of pasteurization to control microbial contamination. Industries began to harness microorganisms for large scale alcohol production, laying the foundation for modern fermentation. The second phase is antibiotic period, that is during 1900 to 1940. The early 20th century brought remarkable developments in microbial fermentation and antibiotics. That is, advances were made in the controlled growth of yeast, particularly for baking and brewing industries. The fed batch culture technique was introduced to control nutrient addition during yeast fermentation, thus improving biomass yield. Chaim Weizmann, during 1912, developed acetone butanol ethanol fermentation using Clostridium acetobutylicum. Products like acetone, that is used in explosives, and butanol, that is used as industrial solvent, became essential during World War I. During 1928, Alexander Fleming discovered penicillin, the first antibiotic produced by Penicillium notatum. During World War II, penicillin production was scaled up using submerged fermentation technology. Penicillin thus saved countless lives and revolutionized medicine by treating bacterial infections. Next comes the phase 3, single cell protein period, that is during 1940 to 1964. This phase saw significant advancements in the production of single cell protein, that is SCP, referring to microbial biomass used as protein source for food and feed. During and after World War II, there was an urgent need for cost-effective high-protein food to address global shortages. Microorganisms like yeast, algae, bacteria and fungi were explored for their protein-rich biomass. Continuous culture systems were introduced to achieve mass production of microbial biomass. This method allowed continuous addition of nutrients and removal of excess biomass, thus increasing productivity. The next phase is phase 4, that is metabolite production period, that is during 1964 to 1979. This phase marked the large-scale production of secondary metabolites such as antibiotics, organic acids and vitamins. Advances in microbial fermentation allowed optimization of conditions to maximize metabolite yields. Following penicillin, other antibiotics like streptomycin, tetracycline, and erythromycin were discovered and mass produced using fermentation. Microorganisms like fungi and bacteria were used to produce citric acid via Aspergillus niger and lactic acid via Lactobacillus species on an industrial scale. This period was characterized by the use of strain improvement techniques, including mutation and selection, to enhance product yields. Next comes the phase 5, that is biotechnology period, that is during 1979 to present. The current phase is defined by advancements in genetic engineering, RNA technology, and biotechnology. Scientists began modifying microorganisms at the genetic level to enhance their productivity and create novel products. Microbes like Escherichia coli and Saccharomyces cerevisiae were genetically engineered to produce human insulin and growth hormones. Microbial systems are now used to produce vaccines, monoclonal antibodies, and therapeutic proteins. Pathways within microorganisms are manipulated to increase the production of metabolites like biofuels, bioplastics, and vitamins. Microbial enzymes were widely used in industries for applications in detergents, food processing, and textile manufacturing. Microorganisms are being developed for the production of bioethanol, biodiesel, and biogas as renewable energy sources. Microbes are applied for bioremediation, wastewater treatment, and degradation of pollutants. Thus, the history of industrial microbiology reflects humanity's ability to harness microorganisms for innovation and progress. From producing alcohol in ancient times to developing life saving antibiotics and now creating genetically engineered organisms, each phase has contributed to transforming industries, medicine, and the environment. The current biotechnology period holds promise for the sustainable and technologically advanced future. With this short note, we shall conclude this session. Thank you so much for your patient listening. We shall meet in the next forthcoming session with another useful content. Thank you.